exciting educational content brought to you by Chrysolite Tutors. Today we'll be looking at MTH 106, Mathematics for Management Sciences Part 2. And we'll be on the Unit 2 today, and we're looking at basic set operations. In this topic, we'll be covering set operation like union, intersection, difference, complement, and we'll look at operations on comparable sets. So if you are not tuned to subscribe to this channel, please stay tuned, subscribe to the channel, and let's go through these topics, objective that we have today to the end, and you will be glad you did. So I'm going to, by way of introduction, say that we'll see set operations performed on sets, in a simple arithmetic. These operations simply gives sets a language of their own. Like in arithmetic, you have operations like addition, subtraction, multiplication, division, and so on. Yes, so these are the arithmetic operations. But in sets, you have operations like union, intersection, difference, and so on. So we're going to look at that as we progress. So what are set operations? Set in arithmetic, like I said, you know about addition, subtraction, and the rest. Okay, so but for set, you'll be looking at things like union, intersection, difference, and so on. So we'll dive in straight. What is union? This is union. Spelling union. That is the operation for set. So let me just call it set operations. Okay. Set operations. So the first one we'll look at is number one, union. Union, and the symbol is like this. Union. Okay, so the union of a set A and B is a set of all elements which belongs to A or to B or both. You understand? So there are three conditions there. If I have two sets A and B, the union of the two of them is the resultant set that contains A or B or both. So we denote it by writing this A union B. It will give me a resultant set inside here. This, when you want to start a set, you have a curly bracelet or bracket. So there is a resultant set inside that comes from this operation, union operation. So when we define union, we say that it's a set that comes from the combination of A and B, for example, or you will have sets in A or sets in B. There are instances where it's like that. So let's just quickly get to an example. For instance, if I have, let's say, let S be equals to A, B, I'm listing the element out, C, and D. So, and I have another set T. I will have the elements F, B, and D. F, B, D, and G. Okay, let me just have it like this. Okay, F, B, D, and G. So I'll now say S union T, this is operation, the operation for set operation. S union T will now give me a resultant set that will contain these two. So, but I'm not going to repeat anything, any of the elements. So I see that A is here, A is not there, so I can have it as 1A here. I see that B is here, B is here. Instead of having BB, I will have B. I see that there's C here and there's no C there, so I have C. There's a D here, there's a D there, I have a D. And there's no G here, but there's a G here, I have a G. So you see that the combination of the two sets will give me 1, 2, 3, 4, 5 elements. 5 elements, unique elements that are in both of the sets. So that is the operation union. Operation union. Okay, so and for Venn diagram, it is represented like this. Okay, so with a Venn diagram, Venn diagram, we can represent union operation like this. So if I have the universal set, this is universal set in a box, in a rectangular shape. So U is the universal set. And this U, universal set, has two sets, A and B. So the union is every area shaded that is shaded. So you are shading both A and you are shading both B. So the union is actually every area shaded. Anyone that is not shaded is not a union. So this is the Venn diagram representation of the union of sets. It's very, very, very easy. Okay, so I'm going to also give you the set builder form for union. Okay, so another example that we have here is that if, for instance, let B be the set of positive real numbers, so positive real numbers, and let Q be set of negative real numbers. So then P union Q, that the union of P and Q consists of all real numbers except zero. So you see that union, has come to play here. In set builder form, we can also define union, for instance, A union B as the set containing the element X such that X belongs to A and X also belongs to B. So that is the way we can see it in the set builder form. Is the element X such that X belongs to A and X also belongs to B. Okay, so we'll go ahead and make two deductions from this subtopic union, that is the operation union. I want to make some deductions, two remarks quickly, so that when you see it in your objective, you'll be able to know what it means. So remarks on union operation. Okay, so the first remark is that, okay, from the definition of union of two sets, that is A union B is the same thing as B union A. This is commutativity. That means I can change the position and the set remains the same. I can change the position and the set remains the same. So that's the first remark. Second remark is that for both A and B, both A and B are always subsets of A and B. That is, A is a subset of A union B, and B is a subset of A union B. You know what subset is? It means that A is inside the two of them. For instance, now I have this Venn diagram again. And this is A, this is B. This is A here, this is B. A union B is this shaded part. Remember, I drew it before on Venn diagram. Understand? So this shaded part is a unit. It's a unit of itself. So A belongs to or is a subset of this. So this is a subset of this whole thing. And again, B is a subset of this whole thing. So that are the two remarks. We go into the next operation, which is intersection. So intersection is a resultant set that comes if two sets operate. There's an operation between two sets, and the resultant is that the elements that are in A are also in B at the same time. So this is the symbol for intersection, and if I have A intersection B or A intersect B, it means that the set will read the elements present both in set A and set B. So this is intersection. This is how it is. So by Venn diagram, I have A and B. Intersection is actually this part, this part, this part. That means there are elements inside of A that are inside of B at the same time. So that's this intersection. Okay, so it reads A intersect B. This thing reads A intersect B. So if I want to write it in words, I will say A intersect B or intersection B. Okay, A intersect B or A intersection B. I think it's more appropriate to use intersection B. So this is how you write intersection of two sets. So I'm going to give us an example. If for instance we have let me do example one. So if I have two sets, let S okay be the following sets. I have A, I have B, I have C, and I have D, and T and T have the following element: F, B, D, and G. Okay, so I have these two sets. S intersects T will be whatever is here that is here. I have B, I don't have A here. I have B, I have B here. So the first element here is B. There's no C here. There's a D. So there are two elements in this intersection set. S intersects T is B and D. Okay, so you can actually go on and get it. The high point here is that for intersection, the element present in all the sets must be common. So it's a common ground. So if I have A intersects B, it means that the set will contain element X that belongs to A and belongs to B. So you have set X that belongs to A and belongs to B. The comma has the same meaning as and. This comma here, the same meaning as and. Just take note of all this for your purpose, for the theory purpose. Sorry, objective purpose. When you are giving objective, you should be able to decode which one is the correct statement. Okay, so it follows directly from the definition of intersection of two sets that A intersects B is the same thing as B intersects A. So again, intersection is commutative. So two commutative operations have come. Union and intersection are both commutative. That means I can swap the position of the sets of the sets, both ways. Okay, so we'll go on to difference. So for difference operation, the difference of set A and B is a set of elements which belongs to A but which does not belong to B. Okay, so we denote it like this: A difference B. So it reads A difference B. Okay, so it's simply A minus B. So if I want to do it in the Venn diagram form, if I have the universal set like this and set A and set B, this A, B. So A difference B is every shaded part here. That means every set that is in A and not in B. I cannot shade this one now because if I shade this one, B has entered it. So it is everything that A has excluding B. It does not have anything to do with B at all. So it's read like A difference B. Okay, so by definition, it is all elements in A. Let me define it. I'm defining these ones. All elements in A, but not in B. A practical example will be like this. Example. So if I'm giving an example, say given that elements or sets, let's say let A be 1, 2, 3, 4, 5, 6, and B is equals to 2, 4, 6, 8, and 10. So A difference B will now be, okay, now look at it this way. What is here that is not here? That is the definition of difference. So I have 1 here and 1 is not here. So I put it in a new set. 2, 2, I cannot put 2. I have 3 here, I don't have 3 here, so I put it in a new set. I have 4 here and I have 4 here, I cannot include it. I have 5 here, but I don't have 5 here, so I'll put 5 here. 6 is there and 10 is there. So the difference is just this. So this is difference. So this is the set, the new set that comes from this operation, difference operation. All right. Okay. So I hope that is clear. So the sets A difference B are normally disjoint. Okay, I'll explain that. Just hold up. Let me. Okay, so let R be set of real numbers and let Q be set of rational numbers. Then R difference Q consists of irrational numbers. Now the difference of A and B may be denoted like this. This difference A and B can be a set that contains element X such that X does not belong to A at all. And at the same time, X belongs to A. At the same time, X does not belong to B. Very, very true. So the difference is a set X such that X can be any element as a number of elements with separation with commas, separated by commas, sorry, such that X now belongs to A but does not belong to B. Okay, now example, or I'll make 2 remarks again. The first remark I'll make here is that if set A contains A minus B or difference B as a subset, okay, i.e. A difference B is equals to, is a subset of A. That's the first remark. Set A contain A difference B. So A difference B is a subset of A. How do I mean? This is the Venn diagram again. A difference B. A difference B is anything that is outside, that is shaded, that is not B at all. So A difference B is a subset of A. So that means this part that is shaded is the part of the whole of A. Okay, that's the first remark. Second remark is that A difference B is a okay, I've said that before. A difference B and A union B and B difference A are mutually disjointed sets. So in this set, A difference B, A intersects B and B difference A are are mutually disjoint. A disjoint set is a set that there's nothing common. Nothing common. So that means intersection is a null set. So if I have A intersect B, now from here again, I want to use it to explain this sentence. Normally, if you see things like this, you understand your objective. Always try and use Venn diagram to explain it. From this is difference. This is difference diagram, Venn diagram. And this is how it looks like. But A intersect B is this one, this center one. And A difference B, B difference A, B difference A are disjoint sets. They don't have anything in common. They don't have anything in common. They don't have anything in common. Okay, so we're going to go into complement. That's the next operation of set complement. Okay, so the complement of set A, the complement of set A is a set that does not, or the set that contains elements that does not belong to A but belong to the universal sets. Okay, so this is how it is. By Venn diagram, I have my universal set like this. So set A is actually, the complement is actually every area that is shaded outside A. See, where my shading is, that's where A complement is. And the notation is this. This is the how to denote it. It's not as if, because it's only operating on itself. It's not like as if it's an operation between, can use to operate with anything. But another thing is that A complement is anything that is not in A. You understand? Denoted by this. So I can have a statement that says that universal set minus A difference A is equals to A complement. This is not minus, this is difference. So this is a remark I'm going to put here. So in case you see it in your OBJ, universal set difference A is the same thing as A complement. A complement. Everything that is not in A. That is what it is. Okay? Okay, so we'll quickly go to the next one. That is operation on comparable set. Operation. Okay, before we go to operations on comparable set, let's quickly look at some examples in the complement section. So let the universal set U be the English alphabet. So the English alphabet has 26 letters, right? From A to Z. So the universal set is A to Z. And let T be ABC. Then T complement will now be anything that is not in these three but in universal set. That's what it means. So T complement is anything that is not in this T but are in the universal set. So I have from D, E, F, G, blah, 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 blah to Z. Understand? So this is T complement. So T complement is actually what is not in the mentioned set, but at the same time is universal set. Another example can be, example 2, under this, I can say that let E be 2, 4, 6, blah, 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 blah. You see, this is just a continuous even number, that's even numbers, understand? And E prime or E complement will now be any number that is not even number, you understand? 9 and so on. Understand? Both of these two are in the universal set of natural numbers. Natural numbers, you understand, is universal set. But at the same time, E prime or E complement will now be what is not in E but is in the universal set. So I hope the universal complement of a set is making sense. So a remark I would like to put here is that the union of any set A and its complement, A complement, is the universal set. Aha. So I'll just put it as a remark under this, because all these remarks are logical. They can use words to twist this for you. So if I have A union A complement, this is U. A union A complement is the universal set, no matter what. No matter what. Okay? Furthermore, set A and its complement are disjoint sets. They don't have anything in common. That's what it means. Number one. Number two, A intersects A complement is empty, nothing inside. It cannot have anything in common. Okay. The complement of the universal set is the null set, and vice versa. The universal set complement is what? A null set. And a null set is a universal complement. They are the same thing. They are the same thing. You understand? These two are the same thing. So I cannot have anything outside universal set. That's why they call it universal. The complement of a set A and the set A itself are the same thing. So see this statement, very, very funny. A complement is A. Just note this one. It's like you are inversing it. You know when you say the Venn diagram like this. Okay. So A complement is supposed to be anything that is not in A, Abi. Right? That's what Abi means. Anything that is in A that is not in A but outside is the universal, is the A complement. Now if you do the complement of this one, you get back this. That's what this one means. Okay. So we'll quickly dive into operation on comparable sets. Operation on comparable sets. Let me put it in the board, which is the last subtopic for this unit. I hope I'm getting the concepts. Operations on comparable sets. Okay, so the operations of union. So what are comparable sets? You have union, intersection, difference, complement. You understand? So the operations on union, intersection, difference, complement have simple properties when the sets under investigations are comparable. The following theorems can be proved. Number one, let A be a subset of B. Then the union intersection of A and B is precisely A. That is, A is a subset of B implies A intersect B is equals to A. Number two, let A be a subset of B. Then the set A and B is precisely B. That is the union of A and B is precisely B. That is, if A belongs to B, then it implies that union of A and B is B. Okay, so we'll try to illustrate these theorems, the first one and the second one with Venn diagram. Okay, so if I have a Venn diagram like this for the first one, I have A and B sort of B is outside and A is inside, right? Okay, so B prime is shaded. B prime is shaded. Is shaded. So B prime is outside. If I have B prime is shaded. Okay, and still on this, if I have another Venn diagram where I have B and A, B is outside, A is inside, right? So A prime is shaded. A prime is shaded. So what's A prime? A prime is anything that is not in A, but in the universal set. Understand? A prime is shaded. Okay, so so if A is B a subset of B, then the union of A and B and sorry, the union of A and B difference A is precisely B. Okay, look at it. Another theory. Quickly. So if A is or B a subset of B, then A union B difference A is B. That is A belongs to or is a subset of B, implies A union B difference A is equals to B. All right. So we summarized by saying that we have been able to dive into basic operations of sets, that is union, intersection, difference, complement on sets, and we worked on the operations using numbers. There are also basic symbols. So let us know the different symbols and the different the way it operates. Let me just put some exercise on the board so we'll look at it together and then we'll wrap up the video. Okay, so quickly we have this on the board. It says if let A be defined as 1, 2, 3, 4, B defined as 2, 4, 6, 8, and C defined as 3, 4, 5, 6. Now find the following. A union B. A union B is the union of this and this. So what is here and what is here at the same time without repeating the terms. Remember, so I have 1 here, no 1 here, I write it down. 2 here, 2 here, I'll take one of the 2. 3, no 3, I take 3. 4, 4, I take one of the 4. There's 6 here, and there's 8 here. So this is union. For A union C, again, what is here and what is here without repeating the element. So I come here, 1, there's no 1 here, I take 1. 2, there's no 2 here, I take 2. 3, there's 3 here, I take one of the 3. 4 and 4 here, I take one of the 4. 5, 1, 5, and 1, 6. So this is a union. That is A union C. Then I have B union C. B union C. B union C again. I take what is common without repeating. So 2, 2, 2, no 2 here, I take 1, 2. Please let's write our brackets well. Then there's 3, there's 4, there's 5, there's 6, and there's 8. And finally, B union B. It does, it's B union B again. So it's just repeating the B. Just repeat what's inside the B. 2, 4, 6, and 8. So this is how simple it can be. Just a logical way of representing numbers. Set has its own language. Today we look at the operations of set, which is how sets can interact using different symbols. So I hope this video has been informative for you. I'd like to thank you for viewing.